Yes, we see your screen.
Perfect. Let me close this. Yes, thank you, Michael. Indeed, so the topic of my presentation today is how to simulate, just a second, how to simulate multi-rotor aerial vehicles, and more specifically, I would like to give a quick overview on computational fluid dynamic analysis. My name is Mateus Teixeira. I am a principal application engineer with Cadence Design Systems. So I just wanted to start the presentation. Let me go to the next slide with the type of engineering problem that we are trying to solve here. So basically, we're trying to answer one question, which is how to predict aerodynamic characteristics of a multi-rotor aerial vehicle using CFD. So there are a lot of words in this sentence here. My goal is to go towards the presentation, and then we address each one of those words in terms of multi-rotor aerial vehicle, CFD, and most importantly, I'm showing here one example on the right-hand side how to predict the unsteady perturbations or aerodynamic perturbations for this type of configurations. Now, what is CFD? In a qualitative overview type of explanation, I would say, computational fluid dynamics can be considered a set of methodologies that use numerical analysis and algorithms to build a digital twin and solve the flow field, reaching an approximated solution for the real flow physics around the body. So what we are actually trying to do here is to use numerical models and computational resources to achieve an approximated solution for the conservation of mass, conservation of momentum, and conservation of energy. So I've included here a few images. This comes from the DLR F6 configuration from the second AIAA drag workshop. And what I'm showing in the bottom is the side-by-side comparison between a wind tunnel test experimental setup for this DLRF6 wing, and on the right-hand side, the CFD solutions, the computational fluid dynamic type of results that we commonly see. So the goal of the engineer performing computational fluid dynamics analysis is to predict the aerodynamic performance, either qualitative in terms of how the flow field looks like and the distribution and the color contours, but also doing quantitative estimations with very precise accuracy on lift, drag, or performance of any aerodynamic body, or it can be also hydrodynamic depending on the flow field, depending on the area of study. On the right-hand side here, I'm also showing another wind tunnel setup, this time for the whole aircraft, including the nacelle. And the goal was to perform a computational fluid dynamic analysis. In this case here, I'm showing on the bottom right, it's what we call a large eddy simulation. And what we can obtain for this type of simulation is the prediction of lift, and also in this case here, I'm showing the isosurface of vorticity and predict how the flow separates from this aircraft. So the value for that for engineers and for companies designing aircraft, for example, is to accelerate their virtual prototyping, accelerate their workflow or the design process by virtual prototyping with extremely high accuracy without spending all the money and expensive wind tunnel test right at the beginning of their design process. It can be also utilized to optimize existing geometry or propose modifications for existing configurations. Now, when it comes to multi-rotor aerial vehicles, we would be talking about vehicles which includes several rotating components that produce lift. And nowadays, they're used for a wide range of applications, ranging from military applications, surveillance, safety inspections, and even drones following mountain bikes for nice Instagram videos, for example. Now, the development of this type of vehicles, the MAVs, they are subject to ever demanding more constraints and requirements. So it can be handling capabilities, operation efficiency targets, and most importantly, noise constraints. So engineers are interested on how much operating these vehicles will disturb the flow field around them and then impact people around the people and populations, even urban areas around these MAVs, right? Computational fluid dynamics can be used to analyze and accurately predict the flow field around MAVs. So I'm showing here on the right-hand side a typical workflow, and I think it's a nice connection to the talk from Matthew here. I start from the very first step when it comes to the CFD workflow with the geometry or a CAD that can come from platforms like Onshape. From the geometry, we build a computational domain in which we specify if there are regions of the flow field that must rotate for our numerical methods, and how much we want to extend far away from the geometry in order to predict the flow field. The next step would be the discretization of the flow space into control volumes, so hexahedral prisms or tetrahedral tiny cells, at which we try to reach convergence for the equations in our numericals or solver for our workflow. And lastly, the last step would be to post-process the results in order to extract meaningful physical information from this configuration at the given operating conditions. Now, when it comes to noise, it is important for us to answer one question, which is, where does noise come from? And here I'm specifically talking about aerodynamic noise. So I built this chart here on the right-hand side that pretty much categorizes the noise, the aerodynamic noise, into two categories: broadband noise and tonal noise. So broadband, you would be considering noise coming from turbulence. So it's a turbulence-induced noise, so chaotic movement of flow field, especially near the wall or in the wake of an airfoil, for example, or also trailing edge vortices emanating from the trailing edge of airfoils or blades, and specifically tip vortices coming from the movement of the flow field from the pressure side to the suction side of a propeller, for example. Now, I want to focus this presentation on the type of noise that we call categorized as tonal. So tonal noise would be noise which is identifiable in certain discrete frequencies. More specifically, in the case of MAVs, we would be talking about blade passing frequency, which is basically a frequency linked to the rotation speed and the periodicity of the propellers in the fuselage. So it determines which is the frequency of the periodic perturbation that someone would see either seated at the fuselage or seated at the propeller, depending on the frame, given the movement of the propeller. So tonal noise, if it is for me to summarize, is at some specific frequency related to the physical phenomena we're modeling, and it can come from the interaction between this rotating component with the fuselage or the flow field itself. More specifically, I'm focusing today on the wake and field interaction tonal noise. Now, to tie the subjects together, CFD and tonal noise, we can use a method for computational fluid dynamics that we name harmonic method. So the harmonic method basically is a frequency domain formulation for computational fluid dynamics that takes advantage of the frequency content of a inherently periodic flow and uses that to accelerate the convergence of your computation. So I'm showing here on the left-hand side a steady state computation. So this is the result that we typically get from computational fluid dynamic analysis. I'm showing here each color represents one value of total pressure over the reference total pressure. And if you're running a steady state computation, you are pretty much looking at a time average solution. So it is, if you average out all the solution across time, you would obtain this stationary solution shown on the left-hand side. Now, with a harmonic method computational fluid dynamics solution, you would obtain an unsteady solution that inherently gives you the harmonic content of your flow field, which is linked to your blade passing frequency. So some things that we're looking at here on the right-hand side is to obtain a perfect continuity of the flow going from left to right across the blade rows in this example here for an actual turbine. And the harmonic method is able to provide us with this information for configurations like turbines, compressors, or anything that presents a periodic flow, as for example, the multirotor aerial vehicles. Now, how does this method work? I'm going to try to give a high-level formulation here. I'm showing the basic equation of the method. Consider, for example, any variable. In this case, I'm showing one example of absolute total pressure. It could be static pressure, velocity, flow field. We are decomposing the flow field of this for this variable into a time average solution in a sum of Fourier harmonics. So if you guys remember Fourier harmonics, they are very important field of study because it allows you to determine the frequency and harmonic content of a given solution in time. So on the left-hand side, I'm showing a solution which varies in space and time. And this is decomposed in the harmonic method into a time average solution, something which is average in time, plus a sum of Fourier harmonics. And the Fourier harmonics are inherently inherent to this type of application because the blade passing frequency is determined by the rotation speed of the blades of the MAV, and the amplitudes are an output of the solver. So we're basically just solving for how much is the amplitude of perturbation given some blade passing frequency using computational fluid dynamics. Now, given this brief theoretical background here, I'm going to try to show one real example for an MAV, starting from a case description, and then the problem we're trying to solve, the mesh setup, which is the discretization in space, the computational fluid dynamics simulation, and the results analysis, what we can take away from this type of simulation. So I've separated for this presentation here an air taxi. So it's shown on the right here. This air taxi is quite big. It's quite large. It's 5.134 meters, 4 meters wide. It can fit around 4 passengers inside. It has 4 propellers, each propeller with 6 blades. Each of those propellers rotate at 3,000 RPM. And the goal of our simulation here would be to analyze the unsteady aerodynamic effects due to this rotation of the propellers. And we can extract extra information I'm going to show at the end of the presentation. Imagine you are seated somewhere below you are standing somewhere below this MAV, and you want to know how much noise you're going to hear from the propeller, if it's acceptable, if you're going to become deaf, or if it's going to be super quiet, silent aircraft. So this type of simulation is going to enable us to get this type of information. As an engineer, I am given the geometry files. In this case, there are STL geometry, can come from OnShape, from Matthew, for example. And then I'm also given the operating conditions of this aircraft. In this case, here is going to be hover flight. But how to apply the harmonic method to this configuration? So the main takeaway of the harmonic method here is the concept of blade passing frequency. So we're looking at, if I'm standing at the fuselage and the propellers are rotating, I'm going to feel a periodic perturbation in time linked to the number of blades. So every rotation of the propeller, I'm going to see a peak and a valley 6 times linked to these 6 blades each of the propellers have. Now, since there are 4 propellers, depending where I am in this fuselage or in the flow field around the aircraft, I'm going to hear more noise, less noise, and superposition or a subtraction of those perturbations in time. So I'm going to use the harmonic method because the flow here will be inherently periodic due to the rotations of those 4 propellers. Now, I mentioned before that I need discretization of the domain. I'm showing in this slide here a domain definition. So when it comes to performing a computational fluid dynamics simulation, it is important to define some domains for our numerical methods that require some rotational formulation. In this case here, I have 4 rotating components, which are the propellers, and I'm creating here semi-spheres surrounding these propellers. These are merely numerical artifacts for us to interpolate the flow solution from one side to the other. So I have 4 semi-spheres, and I have one big sphere surrounding the drone here of 100 meters, and that's the whole extent of my universe, let's say. So if you ask me, how far can you predict the noise of this aircraft? I chose here 100 meters sphere out of it. The choice here comes from your computational resources that you have in hands, and because the larger your spatial domain, the heavier will be your computation and the more time you're going to need to achieve the results. Now, for this 100-meter domain with the tiny air taxi right in the middle there, I've discretized the space into tiny control volumes of the shape of hexahedron. And in total here, I generated 18 million control volumes. Now, as a CFD engineer, I should be worried about the quality of those tiny control volumes, if they are too stretched, if there's an abrupt transition between one cell and the other, because this will impact my numerical prediction of the flow field. I'm showing here a few examples, a few images of this discretization of the domain that we call mesh. On the top right, you have the full domain that we call my universe of computation. And then I zoom in into the elements at the surface of the drone, and you can see here there are tiny little control volumes where the geometry varies a lot. So you could think of the tip of the propeller or the transition between the arm and the propeller. You are also interested on doing volume refinements on regions that you have more interest on studying more specifically the flow physics there. So I've included here 4 spheres around the propeller. I'm showing this image here in order to have more control volumes and more details of the flow field. So just for you to understand, I'm not doing a surface mesh, it's actually a volume mesh, and this is a cut through the sphere, and you can see here every little square representing one control volume for which we're going to try to converge this the Navier-Stokes equations that use in the formulation of the method for the computational fluid dynamics simulation. Now, I mentioned before that we did 2 types of domains, rotating domain and stationary domain. And this slide here is just to show that we have a distinction between the meshes between the 2 sides, the rotating surrounding the propeller and the stationary around that. And between those 2 domains, we have what we call the rotor-stator interface, for which we interpolate the flow field from one side to the other. This is the choice of the engineer performing the simulation. The rotating domain could have other shapes, and there are guidelines on which is the best one to achieve better numerical stability and faster convergence. Now, let's dive into the CFD simulation. This is where it gets interesting because you get the specifications of your flight condition. In this case here, I chose hover flight. So the air taxi is just hovering in air. The propellers are rotating at 3,000 RPM with opposing rotation speeds. And the far field has 1 atmosphere of pressure, and temperature is just sea level temperature, 293 Kelvin. And as I mentioned, hover flight, so magnitude of velocity here is 0. So for this type of simulation, we need to specify all those conditions, and those are called boundary conditions. Some other more advanced settings should also be specified. For example, the type of turbulence model you're using, if it's a RANS type of computation, so Reynolds average Navier-Stokes simulation. Some acceleration techniques, like the use of multi-grid acceleration, and some specific software, in this case here, Cadence Fidelity platform that has a CPU booster feature that accelerates the convergence. So these are more specific to the software itself. Now, what we gain out of this type of simulation. So after converging the simulation, I've obtained a full unsteady solution of the flow field around the aircraft. So what I'm showing here on the left-hand side is a reproduction of that theoretical background slide that I had before, but now applied for this MAV. On the left-hand side, I'm showing the variation in space and time of the unsteady perturbation from the propellers into the fuselage. This is decomposed into a time average solution. So it's an average in time of pressure plus the harmonic content or the amplitude of pressure given a certain blade passing frequency. So let's take a look on the next slide, which gives us some more meaningful information. I've included here 6 images. You can think of them as different frequencies of noise. So 300 Hertz, 600 Hertz, up until 1800 Hertz. And you can imagine that the higher the frequency, the more acute the noise will be. And I'm showing here the patterns of noise on top of the fuselage of this MAV. The red color means an intense perturbation or higher noise, higher amplitude of noise, and the dark blue represents a value of noise, so silence, I would say. If you can imagine, if the passengers are entering through the right-hand side of this air taxi here, you would want a very dark region for across all the ranges of frequencies for this noise. In this case here, I can see that starting from 900 Hertz here, this region gets pretty dark, so which means if someone is there getting in and out of this air taxi, the noise that someone would hear would not be on the high spectrum of frequency, but rather on the lower spectrum, so a more grave noise, I would say. More importantly, you can see here at 600 Hertz, you have a very red region right at the cockpit, so the pilot might be worried here about the noise at this frequency. So this is the type of information that you can obtain out of the simulation. Now, this represents the real flow physics and would need to be validated either with more computational fluid dynamics simulations using different methods and more refined mesh, for example, for what we call a mesh convergence study, or someone would have a scaled model in a wind tunnel in order to validate our numerical results. And once we are confident, we can use this model here to modify the air taxi, maybe change the shape of the arms of the fuselage in order to improve the acoustic footprint in the fuselage. Now, someone would also be interested on knowing how far does the rotation of does the rotation of the propeller affect the flow field? So if you are standing below the air taxi and if you just perform the computational fluid dynamics computation of the steady state mode, you would be predicting a wake here, a region below the aircraft at hover of 13 meters. If you increase the fidelity of your analysis, so a little bit more expensive computation with 3 harmonics, you would be looking at 36 meters of wake below this aircraft. If you increase a little bit further, up to 6 harmonics, you would see that from 3 to 6, you had an overestimation of around 3 meters of the wake. So that helps you predict how far below the aircraft the flow field will be. In this case, I'm showing absolute velocity z in the vertical plane will be disturbed due to the flight of this aircraft. Really interesting. This is for me the most interesting one. This type of simulation would allow you to predict, as I promised at the beginning of the presentation, if you're standing below the aircraft, how much noise would you hear at hover flight given the operating conditions of the propellers at 3,000 RPM. So if you are standing 4 meters below this aircraft, you would hear noise with an amplitude of 115 decibel, which is, for the sake of comparison, something like a chainsaw or a real helicopter or a police siren next to you. So it's quite loud. So considering you are 4 meters below this aircraft, the engineer would have a task there to either redesign the propellers or the fuselage in order not to make you deaf this far away. Now, it could be that someone could argue that this is a full flight condition at hover and you're flying pretty close to the air, and that's why your noise is so high. But this is the type of analysis that this computation would allow someone to perform, right? Now, my final thoughts here, I just wanted to give you a brief overview on computational fluid dynamic analysis. This topic is very extensive. It's a science in itself. Some people argue it's an art, but basically has a huge value to accelerate the product design and improvement of aerial vehicles in terms of performance, efficiency, and range, for example, because it allows us to create a virtual prototype to simulate complex flow fields like the MAV that I showed before, using computational resources in a much cheaper cost than building actual prototypes and doing wind tunnel tests. More specifically, I covered the harmonic method to give a brief overview on how we can leverage the concept of Fourier harmonics for CFD computation. We've analyzed a hover flight conditions using 3 types of computation: steady state, 3 harmonics, and 6 harmonics computation. And we've saw how a frequency domain approach can enable us to get a simple takeaway, even about noise, at a given distance from this MAV. I think that's all I had, so thank you very much.